Section 8.1b, summation notation or sigma notation, simply a shorthand way of writing out entire sequences. So in other words, if I have this sequence a of 1 plus a of 2 plus a of 3 plus a of 4 and so on all the way up through the nth term, I can write that entire sequence in sigma notation. This is the Greek letter sigma. This would be read as the sum from I equals 1 up to n of a of I. The number down here at the bottom is your lower bound. Number up here up the top is upper bound. That is basically telling you your starting point and your ending point for the sequence. So I'm starting at term 1. That's how I would put 1 in here for I. That's how we get term 1 here. I keep going, and now I would put in I equals 2. There's the second term. Put in I equals 3. There's the third term. All the way up to I equals n, which is your upper bound, the nth term, and it's a summation, so we add all of those terms together. Some properties of sums that you should be able to work with. First one, sum of a constant. Sum from I equals 1 up to n of a constant. We can simply take the constant times the upper bound. So in other words, if I have something like the sum from I equals 1 up to 8 of 10, all I do is take the constant times the upper bound. That sum would be 80. Property 2, sum of a constant times a of I. I can pull the constant out in front of the summation if I want to, add up all the a of I terms, then multiply by that constant at the end if you choose to. Third and fourth one are very similar, sum property and addition and difference property. Sum from I equals 1 up to n of a of I plus b of I is the same thing as adding together all of the a of i's, adding together all of the b of i's, and then take those two sums at the end and add them together. And I can do the same thing with the difference. Add up all the a of i's, add up all the b of i's, and then at the end, subtract the two. Okay, evaluating. Sum from I equals 1 up to 5. This tells you that there are 5 terms because we're starting at term 1. Our upper bound is 5. If you can remember, always take the upper bound minus the lower bound and add 1 to it. That will tell you how many terms are in your sequence. In this case, 5 minus 1 is 4. Add 1 to it, there are 5 terms. Our first term is going to be derived by putting 1 in for I. So that's just going to be 3 times 1, which is 3. Second term, put 2 in for I. 3 times 2 is 6. Third term, put 3 in for I. 3 times 3 is 9. 3 times 4 is 12. And 3 times 5 is 15. Add all those up now, and our sum is 45. So again, this is simply a shorthand way of writing out this entire thing right here. Letter B. How many terms are we going to be adding together here? There are 4 of them. 6 minus 3 is 3. Plus 1 makes 4 terms that we are adding together. We're going from term 3 up through term 6. So the third term, fourth term, fifth term, and sixth term, 4 total. What do these terms look like? Well, our first term, we're going to put 3 in for k. So I have 1 plus 3 squared. Next one, put 4 in for k. 1 plus 4 squared. 1 plus 5 squared. And 1 plus 6 squared. Simplify each of these, we end up with 10 plus 17 plus 26 plus 37, and add those up, we get 90. Third one, factorial. This time there are 9 terms. 8 minus 0 is 8, plus 1 is 9. 9 terms that we would have to write out here in this summation. 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, 1 over 5 factorial, 1 over 6 factorial, 1 over 7 factorial, and 1 over 8 factorial. If you plugged all that into your calculator and added it up, you're going to get about 2.718 for the sum. It's important that you know and recognize that the summation notation is simply a shorthand way of writing out all this other stuff. So summation notation is nice because it makes things much more compact when we are writing things out. Each one of these sums can also be done on the calculator, so let's take a look at those. Letter A first. You go into your list menu and over to math. Fifth command down is sum. Select that. Go back into your list menu. Second function stat. Operation. Sequence is the fifth command down. So we are finding the sum of the sequence, and now we put in the part that comes after the summation. In this case, it was 3. We don't need to use I. We're just going to use our X key. And now here's the key, comma, X again. You have to tell the calculator what variable you are working in. So we're finding the sum of the sequence of 3x, comma, in terms of x, comma, lower bound, comma, upper bound, hit enter, and there's the sum of 45 that we are already found by hand. Do the same thing for the second one. List, math, sum, back into your list menu, operations, sum of the sequence. This time our sequence was 1 plus x squared, comma, in terms of x, comma, lower bound, comma, upper bound. From 3 to 6. Whoops, I didn't put an x squared there. Let me go up and correct that. So I'm going to insert the squared there. Hit enter. And there's the sum of 90 that we already found. And finally, the last one. List, math, sum, list, operations, sequence. Try it again here. Sum, operations of the sequence of, this time it was 1 divided by x, and now we need to put in our factorial, math, probability, factorial, comma, in terms of x, comma, lower bound, comma, upper bound. Hit enter, and there's the decimal that you get from there. So again, these can be plugged into the calculator and checked very easily. Make sure you understand, however, how to go from summation form into being able to write out the entire sequence. Okay, number 8. Given the sum from I equals 1 up to infinity of 3 over 10 to the I, find the third partial sum. Okay, this is an infinite sequence. It goes on forever. Our upper bound is infinity, meaning it goes on forever. So when we're asked to find the third partial sum, that's simply replacing that upper bound of infinity now with 3. In other words, we just want to find the sum of the first 3 terms. So we're basically changing the problem to be I equals 1 up to 3 of 3 over 10 to the I power. So if I begin writing that down, first 3 terms, 3 over 10 to the first, 3 over 10 squared, 3 over 10 cubed, which is 0.3 plus 0.03 plus 0.003, which is just 0.333. So there's the third partial sum. Now we want to find the entire sum. Intuitively, this does not make sense that there would be an entire sum, because if you think logically about this, if we are taking some value and we are continually adding another term, it would seem like there would not be an entire sum. Well, if we look more closely at this, we already know what the first 3 terms look like. 3/10 plus 3/100 plus 3/1000 plus 3/10,000 plus 3/100,000 and so on. Or in decimal form, 0.3 plus 0.03 plus 0.003 plus 0.0003 plus 0.00003, and so on, we can see that this is a decimal that is repeating. What decimal is that? Well, it's 0.3 repeating, and we know repeating decimals can be written as a rational number. 0.3 repeating is just a fraction 1/3. So not always will there be necessarily an entire sum, okay? And we'll look more at these types of problems in sections 8.2 and 8.3, where we'll have some formulas that we can use to find out these as well. Last one, write each sum using sigma notation, then find the sum using a calculator. Okay, so we need to look at this and come up with, first of all, how many terms? Well, we see the only thing changing is this value in each term right here. Starts at 1, goes up to 15. There's our upper and lower bounds. What does our expression look like? Well, the numerator always stays the same. The denominator always starts with 1 plus whatever the term number is, so let's call that I. There's our sigma notation. Go to the calculator, plug that in, and find the actual sum. List, math, sum, back into list, operations, sum of the sequence of 5 divided by 1 plus x, comma, in terms of x, comma, lower bound, comma, upper bound. 11.904. Letter B. Rewrite first in summation notation. Okay, first thing that we can see here is that the signs are alternating. From what we've done previously, we know when we have alternating signs, there has to be a negative raised to some power. Okay, the numerator is either 1 or -1 all the way across. So let's start with that. Denominator. Most people can look at that denominator and say, oh, we're multiplying by 2 each time. Do not think of multiplication by 2. If you think about multiplications when you're trying to write these sum formulas, you're going to have a very, very hard time coming up with them. Instead of thinking of multiplying by 2, think of powers of 2. In other words, this is 2 to the 0, 2 to the first, 2 squared, 2 cubed, and so on, all the way up to 128, which is 2 to the 7th power. Again, this starts out as 2 to the 0. So there it gives us an idea of what our upper and lower bounds are going to look like. We're going to go from I equals 0 up to 7 because we're talking about the exponent that we need to put on the 2's. We also need an exponent on the -1 because we do not want it to be negative all the time. We want it to alternate. Well, if I take -1 and I raise it to the 0 power, it's positive. If I take -1 and raise it to the first power, which would be this term, it is negative, which is what we want. So I can combine these really into one I equals 0 up to 7, and I can rewrite this since they're both to the I power as just -1/2 to the I power. Plug that into your calculator. Let's take a look at that again. Stat, math, sum, list, operations, sequence, sum of the sequence of -1 divided by 2 raised to the x power, comma in terms of x, comma lower bound, comma upper bound. 0.664065.